In digital circuits, we have two different types of circuits. The first type of digital circuits is combinational circuits. The combinational circuit is a circuit that, in order to determine the output, we don't need to know a previous value of the output. So no previous value of variables is needed to know what the output of f is. So we can say no previous value of xi is needed to know what the outcome of f is. In this functions, for example, it's a function of different variables x1, x2, up to xn. So like we don't need to know any previous values of variables to determine the output. The next type of circuits we have in logical design are sequential circuits. Despite the combinational circuits, the output of f depends to the value of xi, the value of the variable at the present and the past. So it depends to the value of x at the present and past. One more time. In the combinational circuits, the output depends only on the variables at the present. But in sequential circuits, the value depends to the variables at present and past. So we can say the value of f depends on the value of xi at the present time and past. In fact, how we can have the value of variable in past? Definitely we have to have memory. So this type of circuits, the sequential circuits, it has memory which can keep or hold the data from the past. Okay, so these are two main like category of digital circuits. Now that we know these circuits, we want to start and continue on lectures on combinational circuits. In combinational circuits, we can combine different gates to build new circuits, okay, new combinational circuits. The first device, the first combinational device we will discuss today is called multiplexer. So this one is a combinational circuit. Okay, what is a multiplexer? Which also it's known as data selector, but I prefer to say to call it multiplexer. We show the multiplexer with MUX. Okay, it's a combinational network that has 2 to the power of n data input and control input and 1 output. So before explaining how does it work, let's see how many inputs, outputs it has, and then I will explain how does a multiplexer work. A multiplexer, also known as data selector, is a combinational network that network means network of gates, like the group of gates. A combinational network that has 2 to the power of n data input n control input and an output. Okay, let's see how does it work. Here is a multiplexer. The simplest multiplexer has 2 to power of 1 inputs, which is 2 inputs, input x0 and x1, and select input as control input, which is 1, and 1 output. The output is in fact for this specific multiplexer is S bar x0 plus Sx1. But how does it work? Let me show you. It says if S is 0, if S is 0, x0 will be connected to the output. So S is 0. If S is 0, x0 will be connected to the output. So the output, which is function of control input and the inputs, the output will be x0. If S is 1, x1 will be connected to the output. So if S is 1, x1 will be connected to the output. So it's the basic function of multiplexer. And we call this multiplexer 2 by 1 multiplexer. First of all, 2 is referred to like a number of it refers to the number of inputs, okay? And 1 I will explain later what is 1, but 2 is number of inputs. Okay, so this one is the first multiplexer. Let me see what is the internal architecture or internal circuit of this multiplexer. If I want to do the internal circuit of this multiplexer, we will have this circuit. By the way, before drawing the circuit, let me just talk about this function for a minute. So we see that if S is 0, S bar is 1 and S is 0, so this term will be 0 and the output will be x0. Okay, and we see that if S is 1, this S bar is 0, S is 1, so this term is 0, and so the output will be equal to x1. Okay, so this one is the function of this multiplexer. Okay, so let's draw the internal architecture of this internal circuit of this multiplexer. We have two AND gate. The first AND gate is connected to X0. The second AND gate is connected to X1. Also, the control input is connected to second AND gate and complemented and then connected to the second input of the first AND gate. And these two AND gates are connected to a two input OR gate. So this one is the internal circuit of uh, 2 by 1 multiplexer. Now let's move and see what is how we can design what is like a 4 by 1 multiplexer. So if we design a 4 by 1 multiplexer, we will have this circuit. Okay, 4 inputs, 1, 2, 3, 4. Of course, this multiplexer is 4 by 1 max, and these inputs like labeled x0, x1, x2, x3. We have 4 inputs. How many control inputs? 2 to the power of n is equal to 4. So as a result, n is equal to 2. So we will have 2 select inputs. So we add the select inputs here. It's S0 and S1. And of course, the output is here. So how does it work? It's exactly similar to 2 by 1 multiplexer. We have two select controls, which are S1 and S0, and output. If both the inputs, control inputs are 0, 0, 0, so the X0 will be connected to the output. So the output will be X0. If the control inputs are 0, 1, X1. If the control inputs are 1, 0, X2. And if the control inputs 1, 1 connected to the control inputs, the output will be X3. So this one is a schematic design of a 4 by 1 multiplexer. Now let's do one example. In this example, we want to build a 4 by 1. So 4 by 1 is same as this one. 4 by 1 multiplexer out of 2 by 1 multiplexer. So it says that we have 2 by 1 multiplexers, and we want to build a 4 by 1 multiplexer using this 2 by 1 multiplexers. By the way, we don't have to like build 4 by 1 multiplexer using 2 by 1. We can build 4 by 1 multiplexer like this by drawing the combinational circuits. But in this specific example, it asks us to design it by 2 by 1 multiplexers. So let's do that. So if this one is our 4 by 1 multiplexers, what we need to do, we need to have 3 2 by 1 multiplexers. Okay, and then the first multiplexer is connected to X0 and X1. The second multiplexer is connected to X2 and X3. The output of these two multiplexers are connected to the inputs of the third multiplexer, and the output of third multiplexer is like the main output. And we have, because it has 4 inputs, we are allowed to have 2 select inputs. So one select input is here. We call it select S, let's call it S, not SEL, S1. And of course we have S0 here, which is connected to the first 2 multiplexers. So let's just label these multiplexers, multiplexer 1, 2, 3, and the entire design is a 4x1 multiplexer. 4 is the number of inputs, and 1 is the data bit, like the bandwidth of inputs and outputs, because here we have 1 bit inputs and 1 bit output. We say 4x1. Okay, so let me explain how does this design work. So here we have the truth table, and we have S1, S0, and output. First, let's see S1 and S0 both are 0. What's happening? Because S1 is 0, S1 is 0, these outputs will be connected to the third multiplexers, and because S0 is 0, so X0 will be connected to the output of multiplexer 1. So we see that if both X1 and S1 and S0 are 0, the output will be X0. Okay, so let's erase those highlights. So if both are 0, the output is 0. What if S1 is 0 and S0 is 1? If S1 is 0, again, the first input of third multiplexer will be connected to the output, as I highlighted. Because S0 is 1, the second input of multiplexer 1 will be connected to the output. So the output will be X1. If we continue, we will see that with S1, 1, S0, 0, we will have X2 and we will have X3. And this one is exactly the same characteristic table of 4x1 multiplexer. So this one is a 4x1 multiplexer. Okay, one thing that I should mention about multiplexer naming. So I said that we say 4x1. It means that it has 4 inputs. Okay, so let's see one example here. 4 inputs and 1 output and 2 select inputs. So S1, S0, X0, X1, X2, X3, and F. Okay, so 4 indicates the number of inputs. What is this 1? This 1 shows the data size of each line. How? Let me show you. Let's assume instead of 1 bit for each input and output, we have 2 inputs together called X0, 2 inputs together called X1, 2 inputs together called X2, and 2 inputs together called X3, and 2 outputs called F. Now, if control inputs is 0, these first 2 inputs will be connected to the outputs. If S0, S1 are 1, 1, the last 2 bits will be connected to the output. So if we want to give a name to this multiplexer, we say this multiplexer is 4 number of inputs by 2, the size of inputs. Number of inputs, the size of inputs. Number of inputs, and this one is size of inputs. So if we have another multiplexer here, like 2 by multiplexer with 2 inputs. Let's say we have a multiplexer with 2 inputs. So we have S0. By the way, let me say something. Also, X0, X1, X2, X3, and F are 2 bits. But S1 and S0 still each is 1 bit because it's just control input. Okay, they are not data. So if we have 2 inputs, of course we need one control selects. And so let's say we have data A and data B, and we have the output. And I would say that like the size of each data is 16 bits. 16 bits. 16 bits and 16 bits. Okay, but S1 still is 1 bit because it's just select control. If we want to label this multiplexer, we say this multiplexer is marks 2 groups of input. Each input is 16 bits. So we say multiplexer is 2 by 16. Okay, so we know that now how to label multiplexers. Okay, so the next combinational circuit that I'm going to talk about it is demultiplexer or Demux. It is exactly opposite of the multiplexer. Let's see one demultiplexer. Here we have a demultiplexer. It has one group of inputs, or I say one group of inputs. This because this input can be 1 bit, 2 bit, 5 bit, but one group of inputs. So n one group of inputs, n groups of n groups of outputs. Sorry, 2 to the power of n. 2 to the power of n 2 to the power of n group of outputs and n control inputs. So n. So it's exactly opposite of the multiplexer. Based on the value of the control inputs, the input will be connected to one of the outputs. Exactly opposite of multiplexer. So based on the value of the control inputs, the input will be connected to the one of the outputs. Okay, so let's see one example for example for multiplexer, demultiplexer, sorry, demultiplexer 4 by 1. Okay, so if we want to show the 4 by 1 demultiplexer, it is in this form. Okay, it has one input S0, S1 and 4 outputs. So input, let's call it I. Let me draw it again. Okay, input is called I, outputs are called O1, O2, O3, O4, not O1. Let's start from O0. Always we start counting from 0 in digital circuits. O0, O1, O2, O3, and this one is the truth table or characteristic table. So S1, S0, 0, 0, 0, 1, 1, 0, 1, 1. So the outputs are O3, O2, O1, O0. If R00, O0 is I, the other outputs are 0. If the control input is 0, 1, the output 1 is I, the other inputs are 0. If the control inputs are 1, 0, the output O2 will be I, and the other outputs are 0, and same for the last output. So this one is Demultiplexer 4. Okay, one other thing that I want to explain is about like inverting the data. So if we let's look to the symbol of NOT gate. You see, it's like triangle and a small circle. This small circle means complement. Okay, everywhere you see like it's like a small circle which is not filled it's not like this, it's like a small circle, it means not. Even here this triangle means a buffer that does nothing. I will talk about buffer later, but this small circle means complement. Now here is the point. If we have a multiplexer like this, 2x1 multiplexer, but we add this small circle here, what would be the characteristic table or truth table of this multiplexer? Okay, without this, first let's just draw the characteristic table without the circle. We know that it's x0, x1, it's S, and here is output. We know that if S1, S is 0, and we have only one S, so if S is 0, the output is x0. If S is 1, the output is x1. Okay, so we all know how does 2x1 multiplexer work. Okay, so we know what is this table and what does it mean. But here is a question: what if in this circuit I show it including this small circle like this? If I add this small circle here, it means that all the outputs will be complement. So if S is 0, the output will be X bar. If S is 1, the output will be X1 bar. So anywhere that you see this small circle, it means that it has it complements the data. What if we have the same circuit, but instead of adding that circle to the output, we add it to the inputs like this? What would happen? Okay, again, we have x0. This x0 transfers to the inside of the multiplexer. Because we have this small circle, we will have x0 bar in the input. And x1 also will be complemented, and we will have x1 bar. Now if we draw the table, the characteristic table, we see that if S is 0, x0 bar will move to the output. So we will have x0 bar. If S, I said x, sorry. If S is 0, x0 bar will move to the output. If S is 1, as we see, x1 bar will move to the output. And if we compare these two, we see that they were exactly same. So both of these circuits do the same thing. So this circuit is exactly equivalent of this circuit. Okay, so be careful about these dots. And the last thing about this complement, let's go back to this design, to this multiplexer. I want to say, what if we have the small circle in the input? So definitely the truth table will be changed to this form. Okay, and now what if we have these small circles here? Okay, of course, again the input will be complemented, but one other thing's gonna happen, because before these small circles the other inputs were equal to 0, but because now all the other outputs are equal to 0, but here because all the outputs have that complementer inverter, all of them will be changed to 1. So this one would be like the truth table of this device. Okay, so be careful about those inverters which are represented with this small circle. Okay, so one more time, I said that because for all outputs we have inverter, so all these zeros also will be converted to 1, as well as the input. Okay. The next combinational circuit which we will talk is called the decoder. Okay, we know that all the like information are represented in like binary codes. For digital systems, we represent the information by binary codes. Like if we have n bits, we know that this n bits is capable of representing up to 2 to the power of n like coded information. Okay, so n bit can be represented like can be represented up to 2 to the power of n information or data. A decoder is a combinational circuit that converts the binary information from n input line, to the maximum of 2 to the power of n unique output line. So a decoder is a combinational circuit that converts binary information from n input line to a maximum of 2 to the power of n unique output. Okay, so by the way, the output of encoder decoder can be less than 2 to the power of n, which we will discuss later. So let me just again write the definition of decoder. We can say a decoder A decoder is a combinational circuit that converts binary information from n input lines to a maximum of 2 to the power of n unique output lines. Like if the m bit coded information has unused combinations, the decoder may have less than 2 to the power of n outputs. Okay, I will explain it in examples. So this one is the definition of a multiplexer, a decoder. Let's see how we show a decoder. The decoder, we show it with rectangle, and it has n inputs. Let's call it W0, W1, and 2 to the power of n outputs. Here it has 4, so Y0, Y1, Y2, Y3, and that's it. There is no control input. So this one is 2 by 2 to 4 decoder. Okay, 2 to 4 decoder. 2 is the number of inputs and 4 is the number of outputs. The truth table of this decoder is in this form. We have W1, W0, Y3, Y2, Y1, Y0, 0, 0, 0, 1, 1, 0, 1, 1. If the inputs are 0, 0, it is like the value of 0, and it says that the output number 0 should be activated. So we say the output number 0 will be 1. The input's not transferring to the output like multiplexer. So just it's activating the output. So output will be activated to 1. In multiplexer, whatever we had in the input moves to the output. But in decoder, these inputs just determines which output gets activated. So and the other outputs are 0. If inputs are 0, 1, the output number 1 will be 1, and this one is the entire truth table. And if, for example, we have small circles here, everything in the output in the right side of the table will be flipped. So 1, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 0, 1, 1, 1. So you see that the output completely like complemented. So without those small circles, we have this design, and if we try to write the functions, we can say that y0 is omega 1 w1 bar, w0 bar, y1 is w1 bar, w0, y2 is w1 w0 bar, and y3 is w1 w0. And now we want to design this circuit. Let's just design the circuit together. We use 4 AND gates. W0, W1, so this one is Y0, which is W0 bar, W1 bar, Y1 is W, let me just correct it, W10, W1 bar, W0, so W1 bar is coming from here, W0 can be provided from this side of the connection. Y2 is equal to W1, W0 bar, W1, W0, okay, oh my, what's going on here? Okay, so W1 and W0 bar, and Y3 is W1, W0, which we can get this data from here and here. Okay, so this one is a design of a 2x4 multiplexer. Okay, so we have a multiplexer. What we see in this design, this multiplexer, oh, sorry, it's not multiplexer, decoder. This decoder is always active. So any inputs will be like determine the output. It's useful to include an enable input. Enable input in a like in a decoder. When the enable input is set to 1, the decoder behaves like sets the output based on the input. But if the like enable input is disabled, then none of the outputs are like asserted. None of them are changed. So all of them will be remain 0 if the enable is 0. So enable input turn off, turn on the circuit. If the enable is on, the decoder is working based on this truth table. If enable is off, all the outputs, regardless of the input, are equal to 0. Okay, so this one is enable. So let me write it down. It is useful to include an enable input, which we usually show it with en, e sub n, in a decoder circuit when enabled setting En equal to 1, the decoder behaves as presented above. But if it's disabled, by setting En equal to 0, then none of the outputs are asserted. Okay, so before showing a decoder with enable input, the enable input can be added to multiplexer and demultiplexer circuits as well. It's not just dedicated, or it's not just for decoder. Any combinational sequential circuit can have enable input. Okay, so we can have enable input for multiplexer. If the enable is active, the multiplexer behaves as described. If the enable input is 0, the multiplexer is not working, so there is no output. So enable input can be added to any circuit. So here I want to I show a 2x4 decoder with enable input. So this one is inputs W0, W1 and input enable, and we have 4 outputs: Y0, Y1, Y2, Y3, and the table, the truth table is here. We should add enable as one of the inputs, W1, W0, and Y3, Y2, Y1, Y0. If enable is 1 and W10 are 0, we will have 0, 0, 0, 1. If 1, 0, 1, 0, 0, 1, 0. If 1, 1, 0, 0, 1, 0, 0. If 1, 1, 1, we will have 1, 0, 0, 0. If enable is 0, and we will have 0, 0, 0, 0. You see the output is off. So no matter what is the omega W1, W0, the output is always equal to 0 because enable is 0. You see, for this part, the decoder is off. Okay, it's off. It's not working. And for this part, of the table, we can say that the decoder is on. Okay, one more thing that I want to mention here: instead of repeating all these outputs which are equal to 0, we can just summarize the second part of the table. Just the first part is same, but for the second part we can say if enable is 0, regardless of W1 and W0. So we show it with X, regardless of values of W1 and W0, outputs are 0. So we can just simply replace the green area with this summarized blue area. So we don't want to have like a big table, so we try to keep the table as small as possible but including all information. So instead of writing this information, I said that if enable is 0 regardless of the value of w1 w0, the output is 0, and these x's are called don't care values. We call them don't care. We don't care what is the value. X means don't care. Okay, so let's just have the internal configuration of this circuit. We already saw the design for decoder 2x4, but including the enable, let's just add enable input to this circuit. In order to add an enable input to this circuit, we need a simple modification. I show this like modification with a red pen. So we add another input enable and convert these two inputs AND gates to three inputs and connect this enable to all of them. So now you see that as long as enable is 0, all the outputs are equal to 0 because there are three inputs AND gates and one of the inputs, which is enable, is equal to 0. If the enable is 1, so these red inputs are 1 and the decoder behaves as presented. Okay, so this one is like the modification for adding the enable circuit. We can do the same modification here for decoder, for multiplexer, which I want you to do that as example, as practice. So try to add enable input for this circuit. Okay, let's move on to the next part. In general, so what we saw so far about the decoder was a 2x4 decoder, but in general form of decoder is here. We have decoder here. We have inputs from W0 to Wn-1. We have one enable, so it's enable, and the inputs are n inputs from 0 to 2. From 0 to n-1 is n, and of course we have 2 to the power of n outputs. 2 to the power of n outputs. And these outputs are labeled from y0 up to y to sub 2 to the power of n-1. Because we have, for n input, we have 2 to the power of n output. So 2 to the power of n, when we start from 0, we can write it in the form of 0 up to 2 to the power of n-1. And now we want to construct some decoders, bigger like decoders using smaller decoders. Let's see some examples. So here we have one example which wants to construct a 4x16 decoder with two 3x8 decoders. Okay, we want to construct 4 by 16 decoder using 2 3 by 8 decoders. The solution, let's have our smaller decoders. Okay, and each decoder has 3 inputs. So let's call it W0, W1, W2. So this one is 3 by 8. Oh, okay. The decoder, we show the decoder with like DEC as well. So decoder, we can show it with DEC. So we have 3 by 8 decoder here, 3 by 8 decoder here. And of course, we have enable input, and we need to have 4 inputs. We complement W0 and connect it to the enable of the first decoder, and connect the W3 to the enable of the second decoder. And the last thing, for the inputs, I connect W0 to first input of second decoder, W1 to the second input of the second decoder, and W2 to the third input of the second decoder. And the outputs, we have n outputs for a first decoder, which is Y0 to Y7, and we have 8 outputs for the second decoder, which we label it Y8 to Y15. So this one is a 4 by 16 decoder built from 2 3 by 8 decoder. Let's just see some let's see how does it work. Let's say W0, W0, W1, W2, W3 all are 0. Okay, what's gonna happen here? Because W3 is 0, the second is off. The second decoder is off because the enable is 0, and the first one is on. Okay, first one is on. W1, W2, W0 are 0, so Y0 will be set to 1. Y0 will be set to 1. Let's just see one more example. So 0 0 0 0. If we continue and let's say we are in this value 1 0 1 0 1 0. Okay, for this one, let's see which Y will be activated. Let me erase these highlights. Okay, first let's look to Y3. Y3 is 1, so because not Y3, W3 is 1, so this decoder is on, this one is off, and because W0, W1, W2 are 0 1 0 0 1 0, it means that the second output will be activated. The third output. The third output is Y10. Y10 is third output, so Y10 will be activated. Okay, so we have constructed 4 by 16 decoder using 3 by 8 decoder. Okay, so I want you to but this decoder doesn't have enable input. It's correct that these small decoders have enable, but those are used as as a selector for the decoders which are connected to W3. But this, if we consider an entire design as a decoder which is 4 by 16, this this 4 by 16 decoder doesn't have enable input. So we can add enable inputs to this. We can add enable inputs to these decoders, and so it's your homework, part of your homework for lecture 4. For lesson 4, part of your homework is here. So you will have some assignments that are posted on Sakai. And in addition of those assignments, you need to solve this homework and upload it with your assignments. So what I want you to do, I want to design a 3 to 8 decoder using 2 by 4 decoders and including enable input. Okay, so first design this circuit for the mentioned size, which is 3 to 8, using 2 by 8 decoder, which is simple. Already we have the solution for other size, so you can just simply design this decoder. But the only thing I want you to think about it is that how you can add a like enable input to this circuit. Okay, so after learning decoder, we can talk about this a circuit which is opposite of decoder and which is called encoder. Okay, so encoder is performs the opposite function of decoder. So it encodes the information into to a more compact form. So it gets one input from 2 to the power of n inputs and generate a compact form of the data. So let's write the definition of encoder. We can say an encoder performs the opposite function of a decoder. It encodes given information into a more compact form. An encoder has 2 to the power of n or fewer inputs or input lines and n output lines. Okay, so we want to see a two, two, not two, yeah, 2 to n binary encoder. So I mean that, let me just, I want to show you 2 to n encoder. So it has inputs from W0 to W2 to the power of n minus 1, and it has y0 to yn minus 1 output. So we can say there is 2 to the power of n inputs and n outputs. Okay, this one is like encoder. The encoders are used to reduce the number of bits in order to represent like given information. Okay, so this one is the encoder. So based on the fact that which one of these outputs are equal to 1, we will have a number in the output. So by the way, at any moment one of these inputs can be on. Only one of omegas can be 1. Okay, at any moment. So we cannot have both omega W's turned on at the same time. So if W, for example, W6 is 1 and the other W's are 0, the output will be equal to 1, 1, 0, 0. Okay, so this one is, so y0 is 0, y1 is 1, y2 is 1, and y3 is 0. So this one is the example for 16 by 4 decoder. 16 by 4 decoder, sorry, encoder. Not 16 by 4, 4 by 16, because it's encoder. So a 4 by 16 encoder, if W6 is 1, the other W's have to be 0 at that moment. So if W6 is 1, the number 6 will be appeared on the output, which is y3 is 0, y2 is 1, y1 is 1, and y0 is 0. So if W11 is 1, the other W's are 0, the number 11 will be shown on the output. Number 11, it's like 8, 2, and 1. So y0, y1, y2, and y3. So this one will be the output of the encoder. Okay, so this one is how does an encoder work? And the next, we have different type of encoders. Okay, we have different type of encoders. That the next one is BCD to 7 segment, like a decoder, which I will explain it in the next lecture.